Hey guys, let's have a conversation about exponential functions. So, I think lately you've probably seen that exponential functions can model lots of real world applications. So, exponential models are going to be really, really helpful to us. So, first, the way we know that is an exponential function is that your variable is your exponent. So, if your x is your exponent, that's an exponential function. Remember that b is your base. Now, just a second ago, I was talking about how exponential functions can model lots of real-world situations. So this number is also your growth or decay rate. Beautiful. Now, A is being multiplied out front, right? Excuse me. So that number out front, if we are in a real world situation, that is called an initial value. So if you're trying to write an exponential function based off of a situation, hopefully that can help you out a little bit. So let's talk about exponential growth. So I'll know something is exponential growth if b is bigger than 1, if my base is more than 1. So times when you'll see exponential growth is like in a bank account with interest. You might see it in population, and not just of humans, but of animals. And also disease, which I think we've seen a lot lately. Exponential decay, on the other hand, the most common spot you're going to see this is radioactive decay. There we go. Active. I can spell, I swear. Okay, so radioactive decay is like when you have some sort of radioactive substance and they have half-lives. So you had 50 grams, 100 grams, and then after so much amount of time, now I have 50. And now after that same amount of time, now I have 25. So I just keep lessening by a half each time. So before we start getting into the ins and outs of it, let's just go ahead and graph an exponential function. So the first one that we're going to graph is 2 to the x power. I'm actually going to move myself to the other corner, so that way I'm not in the way. So my advice when we're going through, just to get an idea of how all this looks, we're going to put in -3, -2, -1, 0, 1, 2, 3. Okay, so when we plug in 2 to the -3rd, remember it's a negative exponent, so he moves to the bottom. So that's really 1 over 2 to the 3rd. So 1 over 2 to the 3rd is 1/8. 2 to the -2nd, have to bring him down to the bottom. So now I have 1 over 2 squared. So 1/4. 2 to the -1st, bring him to the bottom. So I have 1 over 2 to the 1st, or 1/2. Anything to the 0 power is 1. 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. And now we're going to go through and plot those points. So I have a point at 3, -1/8, or -3, -1, or -3, 1/8, -2, 1/4, -1, 1/2. 0, 1, 2, 2, 4, 3, 8. All right. So when we connect all of our dots to make this graph, good enough. Here's what you might notice. If I had 2 to the -4th, I'm just going to get a smaller fraction, right? Or, a lesser fraction. So I'm just going to get smaller and smaller and smaller and smaller and smaller. But is there anything that I can take 2 to the power of to make it 0 or negative? No. So what's happening here is this graph is going to get closer and closer and closer to that y-axis, but never touch it. So let's start analyzing this graph and taking a look at the domain. So remember, our domain is our x values. So looking left and right, I can keep on going to the left out forever and ever and ever. And over here on the right, I'm going to keep on going up forever and ever and ever. Also, to think about it, is there anything that's an oh no no in here? You know, is there anything that I can't plug in for x? I can plug anything I want in for x, so that means that my domain is going to be negative infinity to positive infinity. Now remember, your range is going to be your y values. So my y values, they start right here at 0 and go up, right? But we discussed that we can never actually touch 0, right? So when we're going through and we're finding our range, we're going to start, my y values are going to go from 0 to infinity. But since I never actually touch 0, I should make sure to have a parenthesis there. Now, like we were talking about, right here, the graph is just going to get closer and closer and closer to my y-axis, right? But never actually touch it. When we get closer and closer and closer to something but never actually touch it, that's an asymptote. So I was getting closer and closer to that line, y equals 0. So my asymptote is y equals 0. Now let's look at our intercept. So our intercept is where we cross the y-axis or the x-axis. But in this case, it's going to be the y-axis. So right here, I cross at 0, 1. And then let's talk about increasing, decreasing, and constant. So if we had little arrows on this, or if we had a little man walking up our graph, in fact, I just said up, right? He'd be having to walk up our graph the entire time, right? So that means that we are increasing for this entire time. So I'm increasing from negative infinity to positive infinity. Okay, fun fact. Exponential, logarithmic, trigonometric, radicals, all these different types of functions, they are called transcendental functions, which sounds super duper cool, which they kind of are. But the reason we call them transcendental is that they transcend algebra. We can't write them as polynomials. They have to be something special. So in case you ever see something about talking about transcendental functions and you're like, wow, what makes them so special? They just don't have to be written as a polynomial, or they can't be written as a polynomial. Cool. Now what I would love for you to do is go through and graph and analyze 1/2 to the x. Okay, so what you might have noticed is that pretty much this is the same graph just reflected over the y-axis, right? So he's just kind of flipped around. So when you went through and analyzed, hopefully that we had that the domain was negative infinity to positive infinity, just like before. And our range was from 0 to infinity, just like before. And our asymptote is y equals 0, just like before. And our intercept is 0, 1, just like before. However, what you might have noticed is that if we had a little man walking on our graph, he would have to be walking down, right? So that means that he is going to be decreasing, or I'm sorry, my graph, not the man walking on the graph. My graph is going to be decreasing from negative infinity to positive infinity. So that's a way to show that when your base is 2, that's exponential growth. Or when your base is 1/2, that's exponential decay. All right, next time we'll look at some transformations. Hey, I'm back because we forgot to talk about end behavior. So looking at this graph right here, we're going to look at the left hand and right hand end behavior. So on the left side, that's where x is going to negative infinity. So we'll have the limit as x approaches negative infinity of f of x equals. So let's go and look up at our graph. Over here, when x gets farther and farther, more and more negative, my y's are going up, right? So they're going to positive infinity. So that'll be equal to infinity. On the right side, that's where x is approaching positive infinity. So the limit as x approaches positive infinity of f of x equals. So let's take a look at that side. So over here, as x gets bigger and bigger and bigger, it's just going to flatten out, right? It's going to get closer and closer and closer to my asymptote there at 0. So even though it's going to keep on going, getting bigger and bigger and bigger, it's never actually going to touch 0. It's just going to get super close. So even though it doesn't actually touch, it just gets super close, we're still going to say that that's equal to 0. Okay, now I'm done. Bye.